Hi, welcome to the Brookings Biology video podcast of A Little Chemistry. Before you start this video, I'd like you to push pause, go to the biology webpage, and under slideshows, I'm going to ask you to watch this little video, a little chemistry video first, before you go through and watch the next part of the slideshow. So take a break, hit pause, and I'll see you in just a second. Welcome back. Thanks for watching the video. What we're going to do is talk a little bit about some chemistry that has to do with biology. We watched this little video first. If you haven't done that yet, go back and do that. And this is actually a little bit of a review because you should have learned about some of this in middle school. We're going to talk a little bit about atoms. Remember in our last slideshow, we said cells were the basic unit of life, and atoms are the basic unit of matter. They're the smallest little piece of something that shows the property of that element. And so if you remember back from when you learned about atoms, atoms are made of smaller particles called protons and neutrons. We find those in the center or the nucleus of the atom. And then orbiting, moving around that center, around the nucleus, we have another little piece called electrons. And electrons are still inside the atom. They're part of the atom, but they don't sit in the middle. They orbit around the nucleus in what we call energy levels, kind of like bees buzzing around a hive. Notice after the word proton and electron, I put a little plus and minus sign. Protons are particles that have a positive charge. Think P for positive, P for protons. Neutrons are neutral. They don't have a charge. Their name kind of tells you that. But electrons are negatively charged. So I put a little negative sign next to electrons to help you remember that these particles have a charge on them. If you look in just about any chemistry class, you'll see this little chart on the wall. It's called a periodic table, and each of the little boxes stand for a different kind of element. So you have C for carbon, O for oxygen, Fe for iron, H for hydrogen. And what makes the atoms different, the different kinds of atoms different, is how many protons and neutrons and electrons they have inside. So carbon is different from aluminum because it has a different number of protons and neutrons and electrons. We're not going to worry about all of the atoms on the chart, but what we're going to do is look at atoms that are important for living things. You also should have learned in middle school that atoms can gain or lose electrons. Atoms that have gained or lost electrons have an electric charge on them. Because if you lose electrons that have a negative charge, you become more positive. And if you gain electrons that have a negative charge, you become more negative. So an atom that has gained or lost electrons is called an ion. And so how I can tell an ion from an atom is I make a little plus or minus symbol next to their chemical name symbol. So for example, sodium is an atom that often loses electrons. We don't usually see sodium just by itself as an atom. It usually exists as an ion, especially in your body. And so when I write the word or the symbol for sodium, I always put a little plus next to it, and that tells me that it's an ion, not a sodium atom. Sodium often buddies up with another atom, chlorine, and when it does that, chlorine becomes a chloride ion. And chloride is one of the atoms that often picks up an electron and becomes more negative. So we write the chloride ion symbol with a little minus sign after it. Those two often go together. You have probably seen them on your dinner table. Sodium chloride goes together to make salt, table salt. It's what you sprinkle on your French fries. So what we're going to do is look at some atoms and ions that are important for living things. Number one, carbon. Carbon is one of the most important atoms found in living things, and the symbol for carbon is capital C. Next, we have oxygen. Oxygen is also vital for life. You can't live without breathing in and taking in oxygen. And the symbol for oxygen is O. Another important atom for living things is hydrogen. Hydrogen symbol is capital H. Nitrogen, capital N. Sulfur, capital S. And phosphorus, capital P. Notice it makes an F sound like phone, but it's spelled with a PH, just like phone. So P for phosphorus. Those are the 6 most important atoms for living things. You have other atoms inside of you, but these are the majority of what makes up your body. And we're also going to look at some ions that are important to living things. Number 1 is sodium. The symbol for sodium is capital N, lowercase a, with a little plus to, remember that reminds us it's an ion. Sodium has a symbol that doesn't really match its name, not S, because we used S for sulfur. And so a lot of science words come from Latin. Latin was a language that people who read books were able to speak. If you went to school, you learned Latin. And so a lot of science words come from Latin. And so the symbol Na for sodium actually comes from the Latin name for sodium, which is natrium. We talked about this one already, chloride, Cl negative, -1, and often goes with sodium. Another important ion is potassium. Notice this also has a symbol that doesn't really match the name, not P for potassium, because we use P for phosphorus, K potassium. And that comes from the Latin word for potassium, which is kalium. K for kalium. And notice I can tell it's an ion because it's got that little plus sign. Another important ion for living things is calcium. Notice calcium has a +2, 2 pluses next to it. It loses 2 electrons. Calcium is very important for making your bones strong, your teeth strong. We find calcium in foods like milk. And calcium is also really important for making your muscles work. The last one we're going to talk about is hydrogen. And notice we already had hydrogen over on the other side in the atom column, but hydrogen can also exist as an ion, hydrogen ion, H+. Hydrogen ions are something you also learned about in middle school when we talked about pH, how acidic something is. The number of hydrogen ions determines how acidic a solution is going to be. The more hydrogens you have, the more hydrogen ions you have, the more acidic the solution is. That's we measure hydrogen with a scale called a pH scale. You may have done some testing with pH paper to see how acid different liquids were. And that's what the H in pH stands for. It's measuring hydrogens. And we're going to talk more about that. So we talked a little bit about atoms, and now we're going to take those atoms and join them together to make bigger molecules. Molecules are made by joining atoms together. So for example, if I take 2 hydrogens and 1 oxygen atom, I can join them together to make a water molecule. The chemical formula for water tells us what kind and how many of those atoms are in the molecule. So the chemical formula for water is H2O. I know you've heard that before. H2O. What the H says is hydrogens. There's hydrogens, and the 2 tells you there's 2 of them, 2 hydrogens and 1 oxygen in this molecule. The chemical formula is kind of like a recipe. It tells you how much and what kind of atoms to put in your molecule. If you don't see a little number after the letter, like O, that means 1. In living things, we often have very big molecules. How many of you, when you were little, played with those little tiny cars and trucks? We call them micro machines. Micro means small. Think microscope, micro. The opposite of micro is macro. Macro means big, really big. And a lot of molecules in living things are very big molecules. We call them macromolecules. For example, insulin is the molecule that controls your blood sugar. And look at the chemical formula for insulin. If you look at the model, the little gray circles are standing for carbon atoms. The red circles are standing for oxygen atoms. The blue stands for hydrogen. And look at the formula. 254 carbons go into this molecule. 377 hydrogens. 65 nitrogens. 76 oxygens. Notice we also have a little sulfur. 6 sulfur atoms. That's a pretty big molecule. And it's small compared to some of the other molecules inside your cells, like DNA. Molecules can be shown in lots of different ways, and the way we show it kind of depends on what we want to know about that. So for example, one way to show an atom is this way. If I just want to see what goes into my molecule and how they're hooked together, I can show it in a little stick figure. Hydrogens attach to the oxygen to make a water molecule. Maybe I don't really care how they're attached, I just want to know what's in there. And I can write a chemical formula like this, H2O. Maybe I want to kind of see a 3D picture of how it goes together and the sizes of the atoms. Notice oxygen is bigger than hydrogen. It's got more electrons. And sometimes I want to know what those electrons are doing, and I can draw a little picture that uses dots to stand for the different numbers of electrons. Don't get confused by seeing that in different ways. It means the same kind of molecule, water, H2O. And you're going to see atoms and molecules in different ways this year. So just be aware that sometimes we represent them in a little different shape. Water is kind of a cool molecule because it's a molecule that is what we call polar. Look at the molecule. Oxygen's a lot bigger than the hydrogens in a water molecule. There's more electrons buzzing around this part of the molecule. And remember, electrons have a negative charge. So if you have more negatives on this side of the molecule, it kind of makes that side be a little more negative. And that's what that little symbol there, it means kind of or slightly. There's a slight negative charge on this side, and hydrogens are pretty small. They only have one electron in their energy level, and they share with oxygen to make a water molecule. So there's 2 electrons going around here, but that's fewer electrons than on this side, and so it makes this side over here be kind of positively charged. So we call that molecule with an uneven pattern of electric charge a polar molecule. Think about a magnet that has poles, and the plus side kind of sticks to will be attracted to the minus side of another magnet. And it works the same with molecules. You have more pluses on one side, more minuses on the other, and it makes this molecule act in certain ways. Sometimes molecules have both polar and nonpolar parts in the same molecule. This is a little model, a diagram of the shape of a molecule we're going to talk more about later, which is a phospholipid. And phospholipids kind of have a head part on the top that's very polar. And they have long, very nonpolar tails that hang down. And so it's kind of a mixed up molecule. It has a polar head on one end, but very nonpolar tails, and it makes this molecule act in some very special ways, and it's very important. The way it goes together is very important in living things. We're going to talk more about phospholipids in our next chapter. So we took atoms, we made molecules. What's going to hold molecules together? Molecules are held together by the attraction between those opposite charges. So the kind of minus part of this molecule will be attracted to the kind of plus part on this neighbor molecule, and so the molecules then will stick together. We call those small forces that hold molecules Van der Waals forces, and they're named for the person that discovered them. Some of you may switch to Mrs. Van der Waal second semester. She is one of the other bio teachers at the high school here. The other way that molecules stick together is something called hydrogen bonds. In any kind of a molecule that has hydrogen in it can form hydrogen bonds with other molecules. And the bonds are going to also form between those attractions. The positively charged hydrogen atom in one molecule, like water, for example, kind of pus over here, is going to be attracted to the kind of negatively charged atom in a nearby molecule, like another water molecule. That is called a hydrogen bond, and water is very good at making hydrogen bonds. The kind of plus or the kind of minus part, the oxygen part, will be attracted to the kind of plus hydrogen of a next door neighbor molecule, and they stick together. Of all the atoms that are important for living things, carbon is one of the most important. And the reason is that carbon can join to 4 other atoms at the same time. And that makes it able to form lots of different shapes. Notice hydrogen can only stick to one other thing at a time. In a water molecule, oxygen can join to 2 other things. It can join 2 hydrogens, but that's all it can hook onto, only 2 things at a time. Carbon is special. There's only a very few number of atoms that can join to 4 things at one time. So carbon can form 4 bonds with 4 different atoms at the same time. And so it makes it able to form lots of cool shapes. It can form rings, carbon with carbons in the ring, carbon, carbon, carbon. It can make long chains by hooking lots of carbons together. So it's able to make lots of different molecules, and that makes it pretty important for living things because you have lots of different carbon molecules inside of you. This is a vocab word, organic. Organic molecules are molecules that are found in living things, and they contain carbon atoms. So for example, this is a sugar molecule, contains carbon along with oxygen and hydrogen. What other vocab word did we learn about that kind of sounds like the beginning of this? That's right, organism. Organisms are living things, and organic molecules comes from that same root word. Organic molecules are molecules that are found in living things. We need to talk about a couple more vocab words. Hydrophilic. The word philos comes from Latin, again, another science Latin word. It means to love or like. It comes from it's the same root that makes the word philosophy, to love learning. And so hydro, remember, if we take science words apart, we can kind of tell what they mean. Hydro means water. So hydrophilic means water loving, molecules that like water. And so because water is a polar molecule, other kinds of molecules that are polar, like water, try to be near water and touch or hang out with other water molecules. Things that are polar want to hang out with other polar things. And because lots of the molecules that are inside your cells, inside your body, are polar, like sugars, like DNA, like proteins, it makes it so that water is really good at dissolving all those things because they want to hang out and be near and touch water. The opposite of hydrophilic is hydrophobic. Phobia means to be afraid of something. If you've seen the movie Arachnophobia with all the spiders that come, if you have a phobia of something, that means you want to stay away from it. You're afraid of it. So molecules that are hydrophobic are not polar molecules. We say non-polar molecules. And they want to be near and touch other non-polar molecules. They want to stay away from polar molecules. They want to stay away from water. It's the reason when you paint with oil paint, you can't just wash your brush with water. Oil and water don't mix. Oil is a very non-polar molecule. It's the reason you see oil floating on the top of a puddle after a rainstorm in the parking lot. Oil and water don't mix because oil is a very hydrophobic, non-polar molecule. It's the reason that soap works when you wash your hands or wash your dirty clothes. Soap is one of those combination molecules. It's got a non-polar end that wants to hang out and touch the grease, and it also has a polar end that dissolves in the water. So it makes it so it can grab onto the dirt and wash away. It's kind of like a phospholipid. It's got a polar part and a non-polar part. When we write a chemical equation and talk about molecules reacting with each other, we write it kind of like a math equation. I'm going to add these two things together and see the little plus sign, and a chemical reaction is going to happen, and I'm going to produce, the molecules are going to rearrange, and I'm going to produce these things on this side. So the molecules that react, what we put on the left side of the equation, are called reactants. That kind of makes sense. And the things that I'm going to produce from that chemical reaction are called the products. So when I write a chemical equation, I put the reactants on the left side and products on the right side. We're going to write some chemical equations this year. Remember, all the chemical reactions that happen in cells, that's a vocab word that we learned in our last slideshow, is metabolism. And chemical reactions can join molecules together, but also they can break molecules apart. That's all of those reactions that are happening inside your body to build up or break down molecules is called metabolism. One way molecules can join to make a bigger molecule is by removing a water molecule to make a bond. And because we're removing water, we're going to use a word to call this reaction. Think about what the name means. Dehydrate. When you dehydrate, you lose water. Synthesis means to make something. Synthesis means to make something. So we're going to make a bigger molecule by joining these smaller pieces together and pulling out a water molecule to make the bond. So take a look at this little animation. If this is my molecule, and most molecules in living things contain oxygens and hydrogens along with carbons. And so we're going to just look at the oxygen-hydrogen part of these two molecules. And so if I want to join them together, all I have to do is take the H from one molecule and the OH from the other and remove the water molecule, and then when those atoms get removed, it kind of leaves a sticky end that can join those two molecules together. Let's watch that again. Take the H from one side and the OH, and I'm removing a water, and it causes a bond to form. I'm joining these water or these molecules together by pulling out H2O, a water molecule. So dehydration, synthesis. Dehydrate means to remove water. We're taking a water molecule out. Synthesis means to put the parts together. So I'm going to take the H from this side and the OH from that side, and I put those together to make a water molecule. And now these sticky ends can join together, and I hook the pieces together. So I'm taking a smaller molecule and hooking these together to make a bigger molecule. Okay? Polymerization is a kind of dehydration synthesis reaction. We're taking many small subunits that look similar, and we're going to join them together to make a bigger piece. We do this in a lot of chemical reactions in living things. Take the little subunits and I build a protein. Take the little subunits and I build a piece of DNA or RNA. The little pieces that I join are called monomers. Mono means one. And the big molecule that they make is called a polymer. Poly means many, like polygon in math. An example of a polymer is taking these little building block subunits, we call them nucleotides, the A's and T's and G's and C's, remember that from middle school, and we're going to join them together, those little pieces, to make a bigger molecule, a DNA molecule. DNA is a polymer made out of nucleotide monomers. Chemical reactions can also break molecules apart. And hydrolysis, there's that hydro word again, water, and lysis means to split or break something. So a reaction where we're breaking molecules apart, all we have to do is add the water back into the bond. So hydro, water, lysis means to split or break apart. Let's go back to our little animation. Oh, I'm not going to let us go. Let's go back to our animation. And we'll go backwards. We're going to do hydrolysis. breaking with water. So here's my big molecule. And if I want to break it apart again back into its subunits, all I have to do is add the water back in to break the bond. Hydrolysis, breaking apart by adding water back in. I can break those little pieces apart and go back to being monomers again. Okay, let's go back to where we were. So hydrolysis is kind of the opposite. It undoes dehydration synthesis. Adding water molecule breaks the bonds. I put the H on one side and the OH on the other, and I can break that bond apart and split that little piece off again. So it kind of undoes what dehydration synthesis put together. And we use both of those reactions. We break food apart, and then we use the little subpieces to build new things. And so we use both of those reactions. One important chemical reaction in living things is this one, and that's the reaction that provides you with the energy you need to do lots of things in your body. And it happens by using both of those reactions. Dehydration synthesis to add a phosphate group, remember P for phosphate, add a phosphate group onto the molecule, and then hydrolysis to break the P back apart again. It's kind of like charging up your cell phone battery. We add the P to store the energy, and then I can break the P off again when I want to release the energy and use it to do something in my cell. Breaking a bond using hydrolysis is the way that energy is released from ATP. That's our energy molecule, and all cells use that energy molecule. We're going to talk more about ATP in some other chapters. Living things use both kinds of reactions, the build-up reactions and the break-apart reactions, to get the materials that they need from the food that you eat and use those materials in your body. Water is one of the most important molecules found in living things. The average person is about 60 to 70% water. Most of your cells, most of your body, think your blood, all the tissues are mainly water. Babies are a lot juicier. They have even more water than grown-ups. And certain body parts have even more water than others. For example, your brain is about 90% water. Why is water so important? Remember, water is a polar molecule, and it makes it able to dissolve lots of other polar molecules that are important for living things. It's a good, what we call a solvent. Water can also absorb a lot of heat without changing temperature very much. And that's really important. Remember this vocab word? Homeostasis. Helps to maintain your stable internal, doesn't make your temperature change a lot, because water can take on heat without changing temperature. It's also important in climate regulation. If you're near an ocean, the ocean absorbs heat during the day when the sun shines and gives that heat back at night to moderate the temperature. Because hydrogen bonds can form between water molecules so they stick together, it's very important in how molecules move inside your cells, why water can pour, why blood can pump, and hydrogen bonding between water molecules and between water and other things in your body is very important. Water is also an important reactant and product in many chemical reactions. Remember that dehydration synthesis. We use water, pull out a water molecule to build things. We add water back in to break things apart. That's the end of our slideshow. Thanks for watching, and stay tuned for more about molecules in cells.